So the way this is going to work is that you guys just ask us questions, and we'll see if anybody else in the attendance knows the answer. And we'll also help you with the questions, all right? And if there's long periods of silence, don't worry, we won't care. We'll just sit there. If you have a question to ask Professor Nixon, he's got to go in an hour, 5:30, so load that in the front. Sarah has sent you an email, and will handle your questions about her 2 lectures separately, but the rest of us are all here. And so have at it. Anybody wants to ask anything, just raise your hand, and we can take it from there.
We went quickly through the climate displacement stuff, so if you want me to expand on anything, I'm happy to talk about some of that too.
Incidentally, I'm just coming from a celebration for Suki Manabe, who invented the climate model and won the Nobel Prize in Physics this year. And he's 90 and is a hoot because he predicted what we see today, including the climate sensitivity, more than 50 years ago, all right? And so, and you know, strangely, his model forecasts have been dead accurate. In fact, the Nobel Prize reads for accurate prediction, right? But they haven't improved since 40 years ago. Nobody has improved on his predictions in 40 years, all right? It's that stable, so. Okay.
Take on that one.
Somebody. Sure. The way the greenhouse effect works is that shortwave radiation, that is like visible light, and wavelengths like visible light, that short, that energetic, comes into the planet, hits the ground. Some of it reflects off clouds, some of it reflects off the ground. Some of it gets absorbed by like water molecules and stuff. Some heats up the ground or rocks or gets into trees, gets into water, all that kind of stuff. But eventually, it gets dissipated, it gets lost, radiated as heat. And the heat leaves it as infrared radiation. Remember that when you have a hot thing of iron, it glows very brightly, and then it gets down to really dull red, and then it looks like it's not glowing, but of course it still is, just lower and lower wavelengths. And we're all glowing at lower wavelengths still. Everything is glowing, and that glowing light goes back out to space, and that's the way the planet cools itself. It's radiative cooling. If you get put into space, incidentally, you can see in your mind's eye from a science fiction novel or movie, the person freezing. And the way the person freezes is that all that radiation energy leaves them. It's the only thing that cools you in space. And because there's no molecules to give the heat to. And so that rapid cooling is the power of that radiative cooling, right? In any case, some of that outgoing long wavelength radiation that we can't see gets absorbed by greenhouse gas molecules. And those greenhouse gas molecules then re-radiate it sometime later in all directions. Half of it comes back towards the Earth. And it extends the time that those quanta of energy are loitering near the planet's surface. All right, and it's the same way that the iPhone person was loitering, remember, in the department store, that business? Yeah. So that the quantum energy literally spend more time warming things up. And so there are more of them, more of those quanta wandering around because the greenhouse gases have sent some of them back. That's how it works, all right? It concentrates the amount of energy coming in from the sun, how much time it spends, and thus there's more of it near the surface, actually cools the stratosphere, the high atmosphere, for the same reason. You know, yeah. Okay. Well, the recommendations for practicing converting. So the conversions you're talking about are the conversions from, say, gigatons or tons of carbon to tons of CO2. And for parts per million CO2 in the atmosphere to tons. Well, I guess, I mean, the right way to think about this is, let's suppose I told you that there were 10 parts per million in the atmosphere. How many billion metric tons of CO2 is that? Now, you remember what the conversion number is? It's 777. It's an easy one to remember, all sevens. So what you do is you multiply 7.77 times 10, and you get 77.7, and that's how many billion metric tons are in the atmosphere. If you wanted to convert that into gigatons of carbon, the magic number is 3 2/3, 44 twelfths. 3 2/3. And so you know that gigatons of carbon have to be less than gigatons of CO2, because CO2 has 2 big oxygens on it, and carbon doesn't have them, right? And so you know, if you're a science person, you do this sort of thing all the time. But if you're not, it's useful to think, well, does that 77.7 have to get smaller or bigger? Which does it have to do? Got to get smaller, right? Because it's got to get smaller because we're now only going to count the carbon molecules, not all the oxygens. So that means I have to divide by 3 2/3, not multiply, okay? If I were starting with gigatons of carbon, which would mean 33.7 gigatons of carbon, then I would have to multiply to get back up, okay, by 3 2/3. So I guess that's as much as I can help you with to convert back and forth. That's what you have to do, is you're either multiplying or dividing, depending on whether or not you want the number to go up or down. And in general, the number is going to be smallest for gigatons of carbon, okay? I'm sorry, it's going to be smallest for parts per million in the atmosphere, second smallest for gigatons of carbon, and third smallest, that is biggest, for gigatons of CO2, all right? So just remember that has to be the order, and that's going to tell you whether or not you want to multiply or divide. And there's only 2 possible factors, 7.77 and 44 twelfths, okay? Solve for all what? So yeah, so I did, so in general, I don't ask you to do math calculations on this exam, okay? Because it's just not fair to the diversity of backgrounds. But I also required that you memorize the conversions. And so I do expect you to know, all right, that, so you know, frankly, I don't think I've ever asked anybody to, but I wouldn't feel bad about it. If I asked you, all right, you've got 10 parts per million in the atmosphere, how many gigatons of CO2 is it? And expect you to know that you got to multiply 10 by 7.77, okay? All right. But in general, I'm not going to ask you to do some kind of complicated calculation. You know, calculated the expected discounted utility with a 10% discount rate for all future time of X. No, I'm not going to do anything like that. there aren't going to be problems to work. Yeah. Yeah. I mean, that's pretty brutal, isn't it, right? The right way to think about this thing is the way that an economist thinks about it. And although they tip their hat in the direction of consumption being about more than money, whenever they do it in a real-world application, the consumption is the money, okay? It's like per capita GDP or something like that. And so in recognition of the fact that consumption in year T isn't the same as love in year T, right? They convert the consumption in year T into a utility with some function. And that function has a curviness, and the curvier it is, the higher the CIA is. All right? And remember that the curviness makes the system want to be more redistributive because the poor have more to gain than the rich from an increase in consumption, okay? Then what you do is you take, if you have this utility function, you've got to be able to take beta to the tth power and sum over all future t, all future time. That big sigma thing means sum. Sum this year with next year and the year after that and the year after that. That beta thing is a number less than 1. And you can think of beta as 1 minus the pure time discount rate. Now, you'll remember that I told you that you're going to be able to choose your way around any question related to this, okay? All right? But that's what it is, all right? So if this thing is a 5% discount rate, then DR is 0.05 and beta is 0.95. And so you're putting 0.95 in here. And that means next year's utility is worth 95% of this year's to you, right? And the one after that is 0.95 times 0.95, which is, you know, a little more than 0.9 and so on, all right? Yeah. Okay, well, let me just finish this then. So this then is called the social welfare, right? That's the future discounted stuff. And Ramsey's formula takes account of the fact that there's a lot going on here and tries to come up with a number, does come up with a different discounting scheme that only deals with money, where the utility is all just stuck into where GR is the growth rate in the economy. You can think of it as the interest rate, long-term interest rate. CIA is how curvy the function is, and DR is the, you know, cookies today versus cookies tomorrow thing, right? Pure time discounting. And so what Ramsey's was able to show is that this number, if you take beta $, equal to 1 minus this number, and use it in a formula like that, but without any utility, just raw money, then somehow you've taken care of ethics, okay? Somehow you've dealt with all of this stuff. You've dealt with the fact that the economy is growing. And so there are alternative uses for money, because that's in the GR thing. And you've taken into account your redistributive impulses in this CIA thing. So that's what Ramsey's was all about. And the only reason I told you this arcane and seemingly, I mean, almost bizarre thing is that it's actually the way your government makes decisions, okay? That's the thing. And decreasingly so, I must say, as we get to the point where we're now discussing endgame for the climate problem. That is how to get to the end, how to eliminate all the emissions. It becomes much less important to figure out what's the cheapest way to remove a ton of emissions, because you got to remove them all. And it's all about staging. It's no longer about what's the cheapest thing to do on the margin today, the best use of the money today. It's all, you know, you have to do it all. So most of the schedule is set by when things wear out and need to be replaced. So fortunately, at least in this one area, we're getting away from that. But the government does this across the board. I mean, they use this stuff everywhere. Okay? Now you have a question, yeah? The biological and solubility pumps? Yeah. So remember Le Chatelier's principle. Does anybody remember what the solubility pump is? It's a Le Chatelier's principle thing. It's just that if you have water without any CO2 in it, and you expose it to air with some CO2 in it, the CO2 wants to dissolve in the water. And it's going to keep happening and keep happening. Those molecules are going to keep going into the water. Now, CO2 molecules are also going to be escaping from the water. And eventually, the incoming has to balance the outgoing. And that balance is a chemical equilibrium, right? It's a physical equilibrium. And so the solubility pump, but it depends, of course, on the concentration of CO2 in the atmosphere. If there's just a teeny-weeny bit of CO2 in the atmosphere, only a teeny-weeny bit will get into the water before the incoming and the outgoing balance. If there's a gigantic amount in the air, then a whole bunch is going to go into the water, and eventually have to be balanced by a whole bunch leaving. So if you have an increasing CO2 in the atmosphere, that balance is continually shifting up to more and more CO2 in the oceans, you see? And so the oceans are trying to track the changing atmosphere as it dissolves, because CO2 is soluble in water. And so the solubility pump is simply Le Chatelier's principle working on the balance between CO2 and the atmosphere and oceans as the atmosphere grows in CO2. The biological pump is a different thing. And it has to do with the fact that phytoplankton, that is the little single-celled algae, eat CO2 for a living and turn it into sugar, right? That's photosynthesis. And then they get slaughtered on average after 3 days by a predator. And the most common predator is a thing called a herpacticoid copepod that looks like a little cyclops, one eye, and swims around. And it eats the thing, and then bizarrely, it has feces that are highly dense and they sink to the bottom of the deep blue sea. And so it's constantly the case that that rain of poop is taking carbon that was fixed into the phytoplankton and pushing it all the way into the deep, pushing it all the way into the deep. And that's the biological pump, pushing of that stuff into the deep, away from where it could escape back to the atmosphere if it, for instance, decomposed. See, if the poop floated, then bacteria would get on the poop, and they would eat the poop, and they would turn it back into CO2. And a lot of that CO2 would escape into the atmosphere. But the fact that it goes 2 miles down means it's hard for it to get out again. Okay?
Okay. They'll be focused on the lectures, and with supplementary materials from the short readings. Yeah.
Yeah, and then for my questions, there won't be any questions for the large lecture question that I wouldn't have talked about. So if you remember, from Wednesday, I was talking about a number of underlying moral principles that can help generate obligations and to allocate responsibility. So knowing and understanding those. We talked a little bit today about some of the complexities with climate displacement and what sort of normative challenges those pose. And we worked a little quickly through, but put on the map some from moral perspectives that would try to answer those challenges. So things like that. And then also taking into consideration sort of the role of moral reasoning in light of that. But you can use examples that are coming out of like the more scientific material to help illustrate the points that might be coming out of that. So, and I had attached readings to my lectures, and so I tried to highlight the most important bits from the readings in the lecture, but it could help to go back to those assigned readings that I have for the lecture, and you'll see after re-listening to my lecture or something where that is in the text, and that could be a helpful way to study. Yeah.
Sure, does anybody remember any positive feedback? Anybody remember the ice albedo feedback? Yeah, go ahead. What is it?
Have a lot of really light colored stuff and a lot of sunlight bounces off. Ice, which is less white stuff, which means that less sunlight bounces off, which means that ice melts, which means that.
That's exactly right. So that's the ice albedo feedback, and the strength of the sensitivity is about 0.1. Remember that, degrees per watt per meter squared. And the another one is the water vapor feedback. Water vapor is a greenhouse gas. Temperature goes up, more water evaporates into the atmosphere. Warm air holds more water than cold air, so the water wants to rush into it. And that causes greenhouse warming, which causes the temperature to go up, which evaporates even more water, which causes greenhouse warming, which causes the temperature to go up. So another positive feedback. The final one was the cloud albedo feedback. And you'll remember that we don't really know 100% if that one's positive or negative. The mean of the estimate is that it's a positive feedback. And the idea is that when the temperature goes up, the clouds, mostly in the eastern tropical Pacific, where it's always kind of hazy, change color and become more absorptive of light. And that's a warming thing, just like the ice albedo feedback. Same thing, but it involves the brightness of some ice clouds, all right, high in the atmosphere. But it could be the opposite way, right? It could be that it's a negative feedback. The only negative feedback we really discussed was the CO2 fertilization of plants. The CO2 goes up, and the plants have more to eat, which means there's more plant, which means the CO2 goes up. And that is a negative feedback, because if you add CO2 to the atmosphere, then this takes the CO2 back out of the atmosphere. But it's not a temperature feedback, all right? Yeah, the cloud albedo feedback is complicated, and the main thing you should remember is, and still controversial. I mean, it was a big deal in contrarian circles forever. There was a guy, an MIT professor named Dick Lindzen, who claimed that the cloud albedo feedback was strongly negative and would stop global warming, but then all the measurements didn't show it, and blah, 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 right? And so it's complicated. All right, so I singled out one phenomenon, the Eastern Tropical Pacific clouds, because that's a place where it's really strong what the uncertainty was. Just to give you an idea, I mean, this is really geek stuff, but remember that the energy budget of the Earth, there's 230 watts per square meter of solar radiation hitting a spot on average in the world in a year. So that you can think of that as sort of the global energy input for the Earth. And we're dealing with uncertainties of about a degree. So we're interested in global warming that has raised like 3 of those watts, like a 1% perturbation. When I was teaching at Princeton already and was involved in this stuff, people were actively changing climate model formulations that changed the energy balance of the big eastern part of the Pacific by 100 watts per square meter. And those were viable options. So we didn't know nothing, okay, at that time. We know a lot more now. And it's complicated, okay? It is actually complicated, okay? Oh, yeah. Yeah, so the exam is on Gradescape. Gradescope. Scope-scape, I can never remember. Gradescape's probably, or should be, a video game. Gradescope is an unpleasant experience. It's an exam. Okay, so Gradescope, each question is often divided into multiple pieces, maybe 2, maybe 3. And they're worth a certain number of points, maybe 10, maybe 15. And it says that. And there's space, and you have to write stuff. They're all long answer, writing stuff. Some of them will be a full page, and you can go on the back if you want. You can add pages in Gradescope and so on. But it's just like an essay or short form essay test. There's choice, though. Right? So you don't have to answer all the questions. You get to choose which ones you're going to answer. And we said, what, 3 hours? Yeah, and it's an exam not designed to last 3 hours. So 3 hours is a good, really should give you some time. Unless you have some special dispensation to take longer, keep it to 3 hours, because you're really not going to be improving your answers after that, all right? It won't take you the full 3 hours.
And I was going to say, for the philosophy questions, like I didn't put a word count in. I believe some of Sarah's questions has a word requirement, but for the purposes of my questions at least, I care that you answer the question thoroughly, but I don't have a limit. But you're most likely not going to answer the question thoroughly by writing like 2 sentences, right, or 3 sentences. So, a few paragraphs where you're able to elaborate the argument and that sort of thing would likely be sufficient. And the more sort of examples that you can pull in from what we talked about in class or the reading as evidence for the answer would be good.
It's such a good idea because, if you're a grader of these things, you're looking for evidence that the person knows the answer. And if you read the words and of the sort of general answer, and they're not quite the words you expect, and it leaves you wondering, if you read the example, and the example really is an example of X, that's it. They get full credit. I mean, always. So memorizing some examples is a really good strategy for a test like this.
Yeah, especially when you're dealing with conceptual stuff, right? So we talked about some things and contentions on certain kinds of concepts. So if you're able to pull that out through some sort of illustration, it shows that you understand how that concept is working in the arguments and things like that.
Yes? So I would be astonished if you were, but Sarah, who did the two, well, I mean, for this thing, right, this deal here, I'm not gonna ask you to do a bunch of problems, and you don't even have to, you can talk your way around any question on Ramsey's formula. You don't have to answer, okay? And so it's only if you want to answer it that you could. And there will be one on to answer, I will just tell you that. For Sarah, I've never seen a question that she gave that has that, but she does have, you can email her with any questions. She wasn't able to be here today at like the last minute, so she emailed you all. I don't know if you've gotten that. Did you see it yet? Okay, well, she sent you a strategy for contacting her. And also her TA is here. Yeah.
Hi. So for Sarah, Sarah only did 2 lectures, and the questions are on those 2 lectures. I mean,
But they're not like math
yeah,
problems.
they're not math problems. They're on the concepts, and the best, I think, advice is to come up with an example for everything. I think so. Yeah.
Yeah, I mean,
the
the
main
general
concepts.
strategy for, certainly for my work, and not just about for everybody else's, right, is to go through the take-home points, make sure you understand the concepts, be able to relate the concepts to one another, be able to pull up an example of every concept, all right? And after you can sort of do that at will, then spend your time playing like word association games, concept association games, tying this concept in this lecture through 3 nearest neighbors to that concept in that lecture. And that's just a good way to learn how to integrate the material in a course, okay?
I was going to say, like, if you want an illustration or example, and we talked about this in my precept group, but we were talking about, right, the role of values, even in certain kinds of policy decision-making or certain kinds of choices about how to be spending our resources. And someone in my class, you know, provided a really good example of, we know that methane, right, is going to disappear a lot quicker than carbon, and there are, you know, if we were spending a lot of our resources trying to do methane extraction, it might look like we're dealing with the problem, right? But what's hidden maybe under there is some value of the near, or you know, some other kinds of things about not worrying about like down the line kinds of costs that might be happening. So there is a value judgment being made in that particular case about where you're prioritizing. And so in the arguments that we read with Stephen Gardner's piece about the moral problem, at least in my precept, right, we had this discussion about the intergenerational component being a part of that moral problem, and to not lose sight of the fact that you might think you're solving a particular crisis, but that you might be addressing a particular aspect of it, and by not understanding what values are at play, you might be obscuring the extent to which you actually are, you know, addressing these kinds of things. So that was an example, right, that a student brought in from class that looked at some of the science stuff that we talked about, the different radiative force and how long methane versus carbon dioxide is in the atmosphere, and then saying, like, if a politician is deciding to put all their eggs in that basket of methane extraction, what, you know, there might be some sort of assumptions being built in about what's being valued in that case. I don't know if that
Usually
helps.
what's being valued in that case is that the fossil energy companies are paying the person off.
Exactly.
That's my experience.
And they get to say, look, I'm doing something about it. But,
Exactly.
you know.
That's a dodge.
Yeah.
Right, so see, if you're an oil company and somebody says, you know, your methane's leaking out of your wells all over the place, right? And the oil companies, you know, it's bizarre, but I think I even mentioned this, the machines that they run in the field, those things that, you know, back and forth, a lot of those run on compressed methane out of the well, and they vent the stuff to the atmosphere during the decompression cycle. So they're just running on belching methane into the atmosphere raw. And so fossil energy companies, you know, they're always on the edge of getting rid of all that stuff anyway because the methane's valuable, and they'd rather sell it than dump it into the atmosphere. And so when somebody says our only strategy is methane, you know, right, you get the idea. Sure, if you take a line, and let's call this T max, the maximum temperature of a day, okay? And we could put in X for today, and what was the maximum temperature today? 75, yeah, maybe 72 to 75. Yeah. Californian tells me 72.
Yeah, I would say.
LA in winter.
It's 77-ish I saw as a high, but.
Okay, well, there's some number. Okay, we're going to call it 77 because that's close to 7.77, and it's all sevens. All right, so you got an X there. That's weather. Tomorrow, it's something else. The next day, it's something else. We're down here in winter, it's down here a bunch. We can make a whole bunch of X's all over this thing. Each one is the weather. Now, when we're done, we've done that for like 10 years, and we got like a gajillion X's, okay? And what we do is we turn it into a histogram. And the boxes show how many of the days are in the different temperature bins for the box. See that? That's called a probability distribution. It's the probability that a given day is between that value and that value, is the height of that bar. That's climate. Full stop. Okay. And then you summarize this by saying, well, what's the mean? What's the standard deviation? And maybe some other stuff, right?
That's a good question. Yeah, I think. Yeah, do you want to repeat the question?
No, instant.
Yeah, you do it.
So the example was extinction, and what was the first example that you gave? And climate change. Okay. So to think of those as slow violence, as incremental, attritional, as not instantaneous and catastrophic and conventionally cinematic. Okay. So some people might argue that climate change has nothing to do with violence in the first place. So the argument for saying that it's slow violence is that fundamentally, as I see it, two types of slow violence. There's deliberate slow violence or conscious slow violence, and unconscious slow violence. And so the argument, particularly in the case of climate change, would be that people can outsource the effects over long periods of time, say politicians taking decisions, so that if you're interested in the midterm elections or the 4-year electoral cycle, you can say, well, I can greenlight these particular actions because I know the fallout will be 10, 20, 50, 100 years from now, okay? So it's a way of kicking the can down the road. And so the idea of slow violence is to try to bring some element of answerability to the period of decision making, as opposed to saying violence is something that is instantly recognizable and explosive and so forth. So, I mean, you could make a similar argument, or I certainly would make a similar argument around extinction. If we know what the impacts are, say, deforestation, extinction is, you know, as somebody described it, I think I used in the lecture, a whispering death. That it's not like a landmine going off or something. That it's attritional. But when we understand the sources of extinction or the processes that increase that likelihood, then we could call it a form of slow violence. Yeah. And so part of the question there would be, who are the responsible actors, and how much awareness do they have? And so there are forms of slow violence where people simply don't understand the effects. And this is all the way back to, say, Rachel Carson in Silent Spring. She would be saying, suddenly in the post-World War II period in the US, we have so many new chemicals and chemical compounds circulating, we simply have no idea what the public health and ecological effects of those are going to be. But the choice not to have regulatory mechanisms in place, the choice not to invest in research to try to calibrate the public health effects and the ecological effects could be seen as complicit in a form of slow violence. Yeah.
So super geeky fact. Does anybody know there's one case where a single being made an entire species extinct? Took it from its normal population size to 0 by itself. Does anyone know what that is? Yes. I said being on purpose. Actually, was not a human. So it turns out it was a lighthouse keeper's cat off the coast of Australia, and there was a flightless wren on the island. And during the cat's lifetime, it ate them all. Cat has a name. It's like the hero among cats. They think it's, So that won't be on the exam, incidentally. Yeah. Yeah, that's right.
Logistical question. What is the
Last, this, today is Friday, yeah. Today's lecture, is the last one on. Monday's I'm giving a water lecture on Monday that will not be on the midterm. It's just too close, and besides, we had the review session today. Right. Yes? Yeah, so attribution is a way to talk about how likely an event is now versus later. And what you'd normally use is an odds ratio, right? So let's suppose that climate change made something like Hurricane Harvey's rainfall 3 times more likely, all right? So the odds ratio is 1 to 3. If it was 1 unit before, now it's 3 units probable that you're going to have it. 3 units more frequent. So 1 to 3, 1/3, is what's known as an odds ratio. A fraction of attributable risk is 1 minus that. 2/3, 2 over 3. 1 minus 1/3 is 2/3. So it's 1 minus the probability before over the probability after, right? Right after the. And the reason for that is, what does 2/3 mean? It means I'm sitting here in Hurricane Harvey getting dumped on by all that rain. And I'm saying to myself, how likely is it that that my suffering today is being caused by climate change? And the answer is 2 chances in 3. Because there's 1 chance I would have been sitting here anyway, right? So that's the ratio that's used. The fraction of attributable risk is used in epidemiology, and it's also used in the legal system. Remember, if the drunken driving, at the limit now, it's far worse than this if you're way over the limit, but if you're at the limit, I think the probability of hitting a pedestrian is something like a factor of 20 higher, okay? And that means there's only 1 chance in 20. The odds ratio is 1 over 20, right? 1/20. So 1 minus 1/20 is 19/20, which turns out to be exactly 95%, okay? So it's 0.95. 19 over 20 equals 0.95, so it's 95%. So if you've been hit by a driver driving at the legal limit, there are 95% chance that you wouldn't have been hit if that person hadn't been at the legal limit, see? And that's that's enough for a criminal conviction, right, in our world. A torts conviction is just 1 over 2. So a lawsuit is, balance of the evidence, right, more likely than not, is a 1 over 2 standard, okay? All the way in the back, and then you next. Be against hate. Yeah, next, second. Okay. Yeah, go ahead. So radiative forcing is how much, how strong the greenhouse radiation of energy is per unit mass of a substance. Okay, so a kilogram of CO2, how many watts does it result in being re-radiated down to the surface compared to if it weren't there? And so the radiative forcing is a measure of that. How potent is the greenhouse gas? And when we talk about it, we measure radiative forcing in which the unit of 1 is assigned to CO2, and everything is then relative to CO2. So when I say that methane's radiative forcing is 120, what that means is that it's 120 times more of a warming agent, a kilogram of it in the atmosphere, than a kilogram of CO2, okay? Yeah, so it turns out that the way that this stuff works, it's chemistry, right? It's quantum chemistry, but the bonds on a molecule vibrate, all right? And vibrating molecules that are free to vibrate are ones that, and with lots of modes of vibration, are the ones that are strong greenhouse gases. Symmetric molecules are crappy greenhouse gases, okay? And so methane is a tetrahedron. It's a single molecule, a single atom of carbon and 4 hydrogens. If you look online, there used to be a good picture of a vibrating methane molecule online. And if you look at it and you're a musician, we used to do this around my lab and try to figure out, because it's got this incredibly captivating kind of shimmy with multiple modes of shake. And that's why it's such a strong molecule. It's because it's not simply sort of dipole symmetric. Incidentally, what we eventually discovered was it is exactly the syncopated beat in the bass line of a song called Low Rider, if you've ever heard of it, by War originally. All right, so there's another geek fact for you. So that's why. It has to do with the geometry of the molecules themselves and quantum mechanics, okay? This is Sarah's. Which, yeah. No, go ahead. Yeah, because I mean, yeah, it's, I mean, I've got.
You mean the Green New Deal, yeah,
So you're probably going to want to email Sarah about this to find out exactly what you said. I mean, the difference between a coordination problem and a collective interest problem. In a collective interest problem, you need to have everybody moving in the same way, even if they don't, you know. There are all kinds of problems in which if you start moving, all of a sudden it's to everyone's benefit to move. But until somebody starts moving, it isn't. And a coordination problem is that people actually have to do different things and trying to get them organized to do it effectively. And if they aren't doing it, the benefits of the different tasks don't accrue, right? All right. So this is a general set of concepts, right? But she's going to have said something specific about them. And so the best thing to do when studying for an exam is to find out what she specifically wants you to know about them, okay? It's the best emailer. Oh, yeah, I'm sorry. I forgot you. Well, I mean, I don't have any graphs, but I could, right? But I don't have any graphs. If you're answering a question and you can put a graph in as an example, that's like super duper, right? It's good. But it is also my experience that graphs are either like super intuitive to people, but then sometimes not at all. And so I tend to shy away from a complicated graph and asking you to label all the parts of it, okay? Now I can't, there are precept-specific questions on this thing too, that your precept, and so if you're in like the Q section, or the science with a lab, yeah, there's going to be some graphs probably, okay? But those won't be from lecture. Yes? Oh yeah, so the per capita versus like, so total emissions in like gigatons of CO2 are measured in a country according to protocols set up by the United Nations Framework Convention on Climate Change. I didn't say that, but there are rules for how to do that, okay? And companies have to actually report these emissions. And you can calculate them pretty easily because you can figure out how much fossil came into your country and how much fossil is in storage and the change in storage from January 1 to January 1. And the rest of it's all gone just about. So it's pretty easy to check, okay? And then there's also this business of CO2 equivalent emissions, right? So over some time frame, how much methane is equal to the warming of a kilogram of CO2 is equal to CO2, right, in terms of the radiative forcing. And so you inventory all this stuff using protocols from the UNFCCC and then report it. So is that what you meant? And now if you want to convert those to per capita emissions, all you do is divide by the population size. Yeah, I'm not going to ask you how we know what emissions are from a country because I didn't teach it, okay? Being able to interpret the difference between historical emissions, current emissions, and per capita emissions, that's probably a good idea, okay? Just in general. Because it's people use the units, countries use the units differences to argue different, to try to gain advantage in negotiations. So that poor countries want to use per capita emissions, rich countries don't. Countries with a long legacy of historical emissions don't want to include it. And those with a short legacy do, and so on. So when you want to identify who's responsible, the problem is that the word responsible is itself complicated and multidimensional, right?
I was going to say, just to add to that, right, we were talking about polluter pays principles and things like that, right, on Wednesday. And that when you are looking at some of the ways to attribute, right, responsibility, these were some of these kinds of challenges for views that want to take that, right? Because are you looking at historical emissions? How are you quantifying, right, where that responsibility is being attributed to? And if you remember, there were like fault accounts versus no fault accounts. So this hooks up, right, with the challenge of if you're trying to ground certain kinds of arguments for moral obligations to take on the costs or how the benefits and burdens should be distributed, right? This complicates it depending on which route you go.
So the answer to the second question is roughly, but there's no sort of strict accounting. You know, we haven't gone through and said, you've offered too much choice, right? But we were all following the same general guidelines as to how much choice to offer. So my guess is that the choice is, yeah, pretty similar, okay? And the answer is that you should think of the choice as choice that allows you to steer around a question, not choose from a long list which question you want to answer, right? So it's limited choice, right? Designed to allow you to, given the heterogeneity in backgrounds, you want people to steer around subjects that they're not, that they're at a disadvantage in, right? Yes. Well, in general, questions in a course like this become more integrative the further on in the course you go, all right? And so we aspire to questions that are integrative. In a midterm, my experience is that this is highly limited because there just isn't enough of a sort of a foundation in multiple areas to do it effectively. So I wouldn't expect too much of that across, ethics to science and so on. Although you can expect some of the science questions to have ethical content and some of the ethics questions to have science content. And you can also expect that when it comes time to make up the final, Simona and I will have colluded on at least a couple of questions. Okay.
So basically everything that Professor Bacala said, and that just, if you are able to use or see these connection points where the illustrations you might pull from like a more science lecture help you to account for the nature of the moral question that I'm asking, or it can just be an example. So for example, if I'm asking about certain challenges that come up in the context of climate displacement and in coming up with moral arguments for climate displacement, well, part of the complexities, right, are scientific issues, right? Issues of, slow onset versus quick onset events with displacement. We talked a lot about, those, I have on that slide, those various different kinds of complexity. So those do involve things that you could pick up from. Similarly, when we were talking about today, tipping points, we brought up the conversation of ecological tipping points again, but then in the conversation of these relational tipping points that some of the indigenous climate justice arguments were involving. So it's going to be hard for you to ask a question or to answer a question right on relational tipping points and the importance of that if you don't understand what we mean by ecological tipping points, right, which came out of the science lecture. So that's the level of integration that we're probably getting on the midterm, but will be much more so, I would imagine, for the final. So.
So a concerted action problem. Right before I came over here, I was dealing with a concerted action problem. I was talking to a bunch of insurance companies, and they were freaking out because they were losing money yet another year because of the hurricane incidents had gone way up, and the evidence that the extreme hurricane tail has grown in thickness, and they think their pricing model no longer works. But the problem is that their clients say, unless you give us some of this catastrophe insurance, we won't use you. So they all have to include this stuff. And if they raise prices, they price themselves out of the market. And so they would have to all get together and say, all right, we're all going to do it at once. And if they did, everyone would be better off. But it's actually illegal for them to collude in that way, right? Because it's price setting. All right, so they're stuck. Because even though it's in everyone's interest to move forward, they can't do it, you see? So that's a concerted action problem. Yes.
Sure. Yeah, so we were finishing off stuff that we had started on Wednesday. So the question for people listening on the recording is, what was kind of the main takeaways from today's lecture, which was a continuation part from Wednesday. So obviously the Wednesday lecture, right, understanding these principles. The first part of lecture today that I was talking about was complicating this question of climate justice further by indicating that certain kinds of, accomplishments when we're talking about mitigation or adaptation that we want to be done in a just way, or making sure that the processes are just, may not necessarily be able to be achieved, at least this was the argument in the paper, right, because they might be exclusionary to certain kinds of considerations that are brought up in the indigenous climate justice context. So one major takeaway from that first part of lecture today is to understand why that argument's being advanced by Kyle White there. So understanding what he means by a relational tipping point, why these kinds of relations within societal institutions that would otherwise enable them to be just are problematic, especially when we're looking at urgent problems, right? So there's that tension of us needing to have this like quick temporal response, but in order for it to be just, and in the framework that he's giving of indigenous climate justice, you would need to have not overshot some of these relational tipping points, and that already has happened historically. So sort of the tension there. And then the second part of the lecture, which I was looking at climate displacement, is to sort of understand at this point, what are some of the mechanisms that prompt displacement and that they intersect with a number of things. So understanding that climate can be understood as a threat multiplier, right? You can have both quick onset and slow onset causes, but there is a number of complexities for identifying how someone can be considered someone who's particularly displaced by climate apart from other factors. So there's some complexities there, there's some conceptual complexities there, and then there are some legal limits there. So knowing that there are certain kinds of barriers on how we're even addressing the climate displacement problem because of these number of challenges, legal, conceptual, and even, based on like the empirical evidence of tracking whether or not someone is displaced by climate change. And then how are some of the moral accounts that are trying to grapple with this problem navigating those challenges. So I talked a little bit today about the shortcomings in the international legal protection regime, like why the Refugee Convention is not applying at this point to people making claims for asylum on the grounds that they have been displaced by climate change. So at that point, it's even hard to even conceptualize if someone is a climate refugee when you understand refugee in that technical sense. And then also, we talked about some of the challenges that go into migration decisions to even identify that. And that just displacement itself is going to be complex. It's going to be both internal and external, which makes it kind of hard to measure. And so when you're looking at certain kinds of moral solutions or moral arguments for why we have obligations and then what we ought to do, so those are two questions, you can take multiple routes. So then sort of the uptake, right, that we had towards the end of lecture are, what are some different kind of moral approaches that you can make to this? So some folks want to look at responsibility and make certain kinds of like causal arguments. Some folks make arguments grounded in humanitarian claims. Then there are folks that say, no, we should actually be able to expand certain things like the moral underlying principle of the Refugee Convention. I talked about the principle of non-refoulement. not sending people back in harm's way. And then there are the camp of views, which my own view falls into, which there are certain principles within our practice of the state system, or that can be gotten out of this practice of the state system that ground our obligations to that. So the takeaway from the climate refugee section should be, what are the complexities that are involved in it that make it challenging to address it as a moral problem, and what are some attempts, right, that have been made? And I don't need you to worry about, because we didn't get a lot of time to it, to look at proposed solutions, but those are interesting, and I'm happy to, like, if you're just personally interested in it, let you know some of those kinds of things. But to mainly focus on the nature of the normative challenge of addressing climate displacement in light of these various difficulties that it poses. Yeah. Sure. Yeah, exactly. So that's actually a critique of why most people, well, not most people, why some people argue against views that say that we ought to be utilizing the Refugee Convention as a tool. So, and so there are I'll answer this from a moral perspective, and then also from like a political institutional protection, legal regime protection issue. So there are at least two major camps within philosophy that argue for sort of extending the Refugee Convention. And so those folks are saying that the underlying moral principle in the Refugee Convention, the principle of non-refoulement, remember we talked about why the Refugee Convention was put in place, was to not send people back into harm's way. So some folks think that we can generalize out from that principle to also accommodate climate refugees, quote unquote, right? I'm using it in the technical sense. But to your point, right, why is this difficult? Well, there's a number of things that the convention is, constricted by. First, you can only claim asylum if you're already beyond a border. So you wouldn't be able to do any kind of preemptive protection or addressing, before there's a case of displacement, because folks may not have left. It also is not able to address internal displacement, right, because people haven't extended beyond the border. So there's limitations there. And then there are just general arguments about the limitations of the Refugee Convention even having teeth as an international regulatory force, because, it's already obviously being disregarded in immigration practices. But an important point that I think the Refugee Convention can help us understand about the climate context, even if it's not the best legal device to be used, is that it shows that there are conditions under which there are exceptions to claims to state sovereignty. So normally we understand in the state system that each nation, right, has jurisdictional authority over its territory. We tend to see authority over territory as kind of our understanding of sovereignty. And so people get to decide who gets to come in, who doesn't, right? Who gets to make up our communities, who doesn't, and those are state-based decisions. What the Refugee Convention pointed out that was unique, right, that we didn't have pre-1951, was like, no, there are exceptions to state sovereignty. For example, you can't say, no, you can't come in, if the consequences of you denying entry in that case are to return people back to, harm's way, or places where they're going to be persecuted based on these identity, markers that the convention points out. So, plenty of people fleeing in World War II, like I said, came in, on boats towards the U.S., and the U.S. actually turned boats around even before they got even close to certain borders. Like we turned some boats around in the ocean, expressing certain kinds of like claims to sovereignty. So one thing we might think about of why this is helpful, or why then the Refugee Convention reminds us of this, is that there might be further constraints to sovereignty claims when it comes to addressing climate displacement. And that might be that we have obligations to take communities in, but it also might be that we have, and by we I mean whoever, we're assigning responsibility, but that certain states might have responsibility to offer funding, or not offer, to actually supply funding for certain adaptation mechanisms in places where there is displacement. So this gets to the point that I talked about towards the end, was the question of what do we owe? And there's different disagreements about this, but these can kind of fall into two general camps. There's we owe certain kinds of immigration rights, whether that's asylum claims or citizenship in a new country, right, that sort of thing, or maybe a global passport so people can choose. And then there's the camp of views that argue, and they're not mutually exclusive, that our obligations might require us to actually have provide territory or land. And I don't care that you worry about the difference, but rights to territory and rights to land come apart in the literature. But the idea that we might owe people space and rights over that space as well, which would potentially infringe on the sovereignty decisions of a particular state if you're like, no, these people can still be self-determining in this area. So it brings up those sorts of things. So that was a long answer that tried to cover everything we talked about in the lecture today, but that the Refugee Convention has its limitations, but as an exception to state sovereignty, extends this idea that state sovereignty itself is not without constraint, and climate displacement or climate refugees might be another case in which that kind of constraint is there, depending on how you cash out the obligations. Did that answer your question, or I just want to make sure? Okay. So I can't answer for Sarah's, which I'm assuming you're maybe making mention of some of Sarah's lectures, but in my lectures, I think that in order to answer the questions well, if you, like, for example, if a question is talking about certain kinds of complexities that implicate our ability to morally reason and also then make decisions about what to do about climate displacement, one of those challenges or complexities is that we're lacking a legal protection regime because the Refugee Convention, for example, is like one example that's insufficient. And then you could, be off to the races to talking about why that's the case. But there also could be other complexities that don't have to pinpoint a certain kind of policy or historical example that can allow you to answer that question correctly. So if you're going to be referring to, anything specific, I would be seeing it as an example in order to answer the question.
A good rule, if you think about, put yourself in the perspective of somebody who's only making up a few questions to cover all their stuff. They're not going to waste one by saying, tell me about the Refugee Convention, all right? What they're going to do is they're going to ask you some general issue about for which the Refugee Convention might be a really useful part of the answer. But so learn the concepts and then try to embed some particulars in them.
And especially with, we ran through a lot of moral principles on Wednesday, and we ran through kind of pros and cons. And I know that kind of doing that larger survey of these different ways in which we can ascribe responsibility might seem overwhelming. But if you look back and you go back at, in the lecture slides and stuff, there is a back and forth discussion and debate. If we do this particular, if we follow this particular line of reasoning, there might be some shortcomings there, but it gets us out of these problems. So if there is an illustration or example that might show why one particular view is stronger than another and you want to defend that, you can then pull from the examples in order to illustrate that.
Yeah. I'm not going to ask what is the United Nations Framework Convention on Climate Change. We didn't have a lecture on it, all right? I mentioned a couple of times that the United Nations Framework Convention is the international foundation for international action on climate. And so if I were studying for this exam, I'd I'd want to remember what that thing is, right? That's where the Paris Agreement came from and stuff like that. Now it's, I actually don't think it's going to be necessary for this exam. all right? But it's a useful thing to know. It's like it's the only treaty I ever talked about, right? And all of the stuff, all the negotiations, COP26 that's coming up next month, that's just another episode of the same thing.
Yeah, and you can see in my lectures, for example, like if you go back to the slides, usually I even type like example, right? And then I'll link to whatever institution or treaty or whatever thing I'm talking about. I think we mentioned like human rights language and why a certain principle had an advantage was because it already appears that certain kinds of conventions, and I listed them, use that kind of language and that sort of way to understand the concept. So that was, for some folks, an argument about why that particular principle seemed beneficial, right? Because it's already at play, it seems, in understanding stuff within the convention. So that would be where it would be like an illustration of maybe the strength of a view, as if it already appears. Or it could be a weakness, right? Because there could be insufficient, elements in these conventions and things like that.
This isn't going to be on the exam, but one of the things that worries me the most is that we only have less than 30 years to completely swap out an energy system, and that's like super, super challenging. And, it takes 7 years on average to build a wind and solar facility, primarily because the community pushed back already, and only 11% of them make it through because the community doesn't want the stuff there. Somebody really likes their view, and, people are afraid of that somehow the wind turbine is going to affect their health, and, there's all this stuff, right? And as we become more concerned about social justice and compassion, the remedy is always to make the process much more consultative rather than less. And so you want to find out what the community itself wants and try to help tailor the solutions where they get a share in the say on siting decisions. But that's going to lengthen the time scale, all right? And it's sort of a dueling business. The most radicals on climate change want really rapid action and environmental justice. And the only way to get rapid action is for the government to go in there with a heavy hand and wreck your neighborhood, all right? So I just think there's a bit of a train wreck coming on the left because of that tension.
And that's the exact tension, right, we talked about today in the lecture,
Yeah, exactly.
right? Was that
that's
like...
what, when you were talking, that's
yeah,
what I was thinking.
Yeah, no, that's great.
Yeah.
Yeah.
I was in an EDF board meeting earlier, in the Environmental Defense Fund in New York, 2 days ago, and I talked about this, and it was like news to them because they're like every other philanthropic organization now, diversity and equity and environmental justice, if you're an environmental organization, those are the issues. But also urgency on the climate problem are issues, and there's just no acknowledgement yet that these two, all of these extremely laudable principles are right now in conflict with one another.
Right, like in the paper that we were talking about today, there's this idea where, and Kaiwai kind of bites the bullet a little bit in this article and was like, yeah, well, if we're busy doing the work of creating the kinds of appropriate relations that are needed for just institutions and for justice, we're probably going to miss and hit these ecological tipping points. But if we're talking about achieving justice, we either have to be very honest that we might be falling short of hitting certain kinds of justice requirements if we move too rapidly. And if we move with incorporating this sort of thing, then we might have to understand that certain tipping points might be overshot. And then what do we do there, right? And he kind of offers this kind of solution at the end, not really. I think he's more just trying to illustrate the tension, but it's like, well, we need to understand at the very least that these things work hand in hand, or are at least present in the considerations of justice. But yeah, then we have these tensions that we're going to have to work out. It's like, I feel like the challenge down the pipeline.
Mm.
Yeah. Right, yeah. So even the time frame of what looks like a rapid movement, right, for a particular government. I mean, in the case of climate displacement, just little anecdote, there are communities like in Alaska, for example, or Southeast Louisiana, primarily indigenous communities that are literally like losing like the habitability of the spaces, not even going to work within the lifetime of the people that are there. And there's a lot of contention over the kinds of money that's going to be allocated and what the plans are going to look like. But it's sort of like late stage decision making, at least in 2 cases, there wasn't, they kind of like went over and didn't acknowledge the community's kind of contributions to the proposal and kind of like railroaded it. And so the community just said, okay, well, keep your money. Like, we won't move yet, right? But there obviously comes with huge costs given the fact that the territory is rapidly becoming unlivable. So there is this kind of tension about to what extent you have representation that's both adequate and being able to address urgency. And that's very, very hard when you already have so many situations of distrust based on historical injustices and that sort of thing, and exploitation and land grabs and all that.
Well, people, we're close to out of time, so if you've got one more question, think it up quick. Otherwise, see you on Monday. All right.
Thanks, everybody.